Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep. So let's have a brief recap of what we were studying in the previous class. So we saw how magnetic tunnel junctions, or MTJs, consisting of a thin tunnel oxide sandwiched between two ferromagnetic layers. One is the pinned layer and the other is the free layer, is at the heart of all MRAM devices. If the magnetization in the ferromagnetic layers was in parallel direction, that is, both are magnetized in the same direction, then the MTJ is in low resistance state, whereas in anti-parallel configuration, it is in high resistance state. Now, depending on how you change the magnetization of the free layer, we have two different kind of MRAM devices. The first generation of MRAM devices were called field MRAMs or toggle MRAMs, and the second generation devices were called STT MRAM, spin transfer torque MRAMs. In toggle MRAMs, we saw that the magnetization of the free layer is changed by oystered fields, and therefore write and read paths are separate, which really heavily limits your scalability. However, in the new or the second generation of STT MRAMs, the concept of spin transfer torque is applied and the read and write paths are the same through the MTJ, making the scalability of STT MRAMs much better. We saw that this is possible because by the preferential transmission of spins of the same polarity as that of the hard or the pinned ferromagnetic layer, and reflection of the spins which have opposite polarity, you can accumulate spins in the free layer, thereby applying a torque on the magnetization of the free layer, thereby flipping it. Okay, so in today's class, we will see the third generation of MRAMs known as SOT MRAMs or spin orbit torque MRAMs, and also conclude by looking at the commercialization efforts of MRAMs. So let us begin. So as we had discussed just right now, that in the second generation of MRAMs, the flipping of the magnetization happens as there is a spin filtering that happens through the junction when spins are either selectively transmitted or reflected. In the third generation of MRAMs, the mechanism of the spin segregation is slightly different. The mechanism comes from something called the spin Hall effect, and the segregation happens due to a very fundamental physical interaction called spin orbit coupling. To understand what is spin Hall effect, first let's look at ordinary Hall effect in case we might have forgotten about it. So as we have seen in our basic physics courses, the ordinary Hall effect manifests when you pass a current through any material which has a lot of free carriers, and along with the current that in this case you are flowing through the x direction, you apply an orthogonal magnetic field which is in the z direction. And as a result, due to the Lorentzian force that gets applied on the moving electrons or moving charges within these material, whether it's a semiconductor or a metal, it just should have some free carriers. And we see that this Lorentzian force gets applied on the charge carriers orthogonal both to the velocity of these charge carriers, which is determined by the current direction, and also the magnetic field. And as a result, there is a separation of charge carriers happening at the edges of the material slab. So as you can see that the electrons are deflected to the further end of this particular slab, thereby creating a Hall voltage. So there is a negative Hall voltage in this particular case. And as we have studied, Hall measurements are routinely used in semiconductors to measure the polarity of the majority carriers and also to measure mobility of these majority carriers. However, what happens in the spin Hall effect? In the spin Hall effect, as opposed to the ordinary Hall effect, you do not apply any magnetic field. Spin Hall effect occurs in the absence of magnetic field. And this, although can be seen in almost all the materials, for reasons that we will be describing very soon, are more dominant or clearly seen at room temperatures only for heavy metals. So heavy metals are metals which have very high atomic numbers. So here too, you are applying a charge current in the x direction to this slab, which consists of one of these heavy metals. And what you see is that unlike the ordinary Hall effect, where electrons, irrespective of its intrinsic spin, both up and down electrons were accumulating on the side of this particular semiconductor or metal, in the spin Hall effect, the upspins are deflected to one edge of the sample, whereas the downspins are deflected to the other edge of the sample. So this happens because of this effect called spin orbit interaction or spin orbit coupling. It is also important to know that since the spin segregation and therefore the spin current happens orthogonal to the direction of the flowing charge current, therefore not only is there a spin segregation at these interfaces that I have marked out, but also there will be a spin segregation on the top and bottom interfaces of this heavy metal layer. This is because even the top and bottom layers, which are the XY plane, are orthogonal to the flow of the charge current. So now let's try to understand what is this spin orbit coupling. So spin orbit coupling is a relativistic quantum mechanical interaction between the particle's intrinsic spin and its orbital motion. So what happens is that as an electron orbits the nuclei, its motion creates an internal magnetic field. Remember, even the electron possesses an intrinsic spin which has its own magnetic moment. This interaction of the electron's magnetic moment with the magnetic field generated by its own orbital motion is called spin orbit coupling or spin orbit interaction. Now, to understand this phenomena better, let us look at a classical analog of spin orbit coupling, which is known as the Magnus effect. And almost all of you must have seen the Magnus effect or experienced the Magnus effect, especially if you are a football fan. So these footballers who are trained to hit the ball in such a way when they take free kicks that in addition to giving the ball a linear motion, they also are trained to kick the ball such that there is a spin motion which is given to this football. As a result, what happens is that when the spinning ball having a rotation motion and a linear motion interacts with the wind direction, the top surface has wind moving in the same direction, whereas the bottom surface has that moving in the opposite direction. So there is a net deflection or a net translation happens in the sideways direction in addition to the linear motion, and this is called the Magnus force. Now imagine if the ball was spinning anti-clockwise instead of clockwise, the Magnus force would have been in the downward direction. So the similar thing is happening also in spin orbit coupling. You can imagine that the spin of this football is somehow analogous to the intrinsic spin of the electron, and these field lines that you are seeing is analogous to the magnetic fields that are generated due to the orbital motion of these electrons. However, it might be worthwhile to look at the spin orbit coupling in a little bit more detail. So let us imagine that an electron is moving through the lattice of a heavy metal. So as you see, as the electron moves in the lattice of a heavy metal consisting of these large positively charged ion cores. If you think that you're sitting on the electron or from the reference frame of the electron, the electron feels as if the ion cores are moving in the backward direction. So just as when you are in a moving train, you feel that the trees and the buildings are moving in the opposite direction. From your frame of reference, the electron feels that these positive ion cores are also moving in the opposite direction. Now, as we know that any moving charges creates a magnetic field, this pseudo-magnetic field is experienced by this particular, and this pseudo-magnetic field causes a deflection or scattering of different spins in altogether different directions, as you can witness from this particular animation. While the up spin moves on to the bottom surface of the metal, the down spin moves to the top surface of the metal. Of course, if you would want the down spin to segregate out in the bottom surface of the metal, you just need to reverse the motion of these electrons, or you need to reverse the supplied charge current. Also important to note that since this is a relativistic effect, this is more clearly seen only in heavy metals such as platinum, tungsten, iridium, tantalum, because in heavy metals, the outer shell of electrons move at very high speeds, reaching which are comparable to relativistic speeds or the speed of light. And therefore, the spin orbit coupling, being a relativistic effect, is directly proportional to the fourth power of the atomic number. And that is why this effect is predominantly seen only in heavy metals. However, for the purpose of our course, it suffices to understand that when you pass a charge current through a heavy metal, due to spin orbit coupling, there is a segregation of electrons of different spins in the opposite directions. And this segregation of spins in the opposite directions is what is utilized to flip the direction of the magnetization of the free layer in the context of SOT MRAM based devices. So let us understand with a simple schematic. In front of you, you have a magnetic tunnel junction with a pinned layer and a free layer separated by a tunnel oxide. And in this case, the magnetization in the free layer and the pinned layer is in the anti-parallel direction, and therefore this MTJ is in a high resistance state. So how do we go from the high resistance state to the low resistance state, or how do we do the set operation? What you do essentially is you flow a current through the minus X direction. When you flow a charge current in the minus X direction, due to spin orbit coupling, this heavy metal segregates the spins of one direction on the top surface of this heavy metal layer, whereas the spins of the opposite direction are segregated on the bottom interface of this heavy metal layer. Now this torque, which is applied by the segregated spin of the electrons, flips the magnetization of your free layer, thereby changing it from the anti-parallel state to the parallel state, which is now making the device switch from high resistance state to low resistance state. Now, how will you make this device flip back to the high resistance state? It's very simple, as we had discussed. If we flow a charge current in the opposite direction, the opposite orientation of spin segregation happens. The upspin electrons now gather on the top interface, whereas downspin electrons gather in the bottom interface. The accumulation of these upspin electrons again apply a net torque on the magnetization of the free layer, thereby flipping the device from the parallel configuration back to the anti-parallel configuration. And this is how the set and reset or write happens in a spin orbit torque MRAM device. As you may understand that unlike the STT MRAM devices, the read and the write paths in a spin orbit torque MRAM device are segregated. The read and the write paths are completely separate, whereas the write operation happens through this heavy metal layer by controlling the polarity of bit line. You can control the direction of the current which flows through this heavy metal layer. Therefore, the word write line is connected to this particular MOSFET. Whereas the read operation happens just as it does in your STT MRAM, which is through the magnetic tunnel junction. Therefore, the read word line and the write word line are separate, and the read-write paths are also separate. Because SOT MRAM devices are competing against STT MRAM devices for widespread commercialization, it may be worthwhile to compare these technologies across different parameters. So, the scalability of STT MRAM devices, as you can understand, is much better compared to SOT MRAM devices, simply because in STT MRAM devices, the read and the write paths are the same. Therefore, you need only one transistor in the case of STT MRAM devices, whereas in SOT MRAM devices, you need two different transistors. Therefore, the area scalability of SOT MRAM devices is poorer compared to STT MRAM devices. However, when it comes to all other parameters, we will see that SOT MRAM devices are actually better than STT MRAM devices. Why is this the case? First and foremost, we see that although STT MRAM devices offer almost 10 to the power of 8 read and write cycles, the endurance of SOT MRAM devices is even better. People have shown almost 10 to the power of 12 read and write cycles when it comes to SOT MRAM devices. This is because by the virtue that the write does not happen through the magnetic tunnel junction in the case of SOT MRAM devices, the electrical stress is not applied on the tunnel junction, and therefore the degradation of the tunnel oxide of the tunnel junction is much lesser in SOT MRAM devices compared to STT MRAM devices. Furthermore, the power consumption in SOT MRAM devices is expected to be lesser as compared to STT MRAM devices because the write happens through a heavy metal layer instead of a tunneling barrier. Therefore, with smaller densities of currents, you would be able to do the write operation. Furthermore, the speed of SOT MRAM devices is also much smaller as compared to STT MRAM devices, where STT MRAM devices have a speed of 5 to 20 nanoseconds. There have been demonstration of sub-nanosecond operation in SOT MRAM devices. However, despite these advantages of SOT MRAM devices, they are still in the phase of maturity, and STT MRAM devices are still the preferred choice for large-scale commercialization, primarily because of better bit density and cost per bit that STT MRAM devices have to offer over SOT MRAM devices. Next, we look at the commercialization roadmap of the MRAM devices. While the technological advancement in MRAM devices are happening from mid-1990s, the commercialization of MRAM devices only started in mid-2000 with the first demonstration of toggle MRAM devices in 2006. So the first demonstration of toggle MRAM devices or field MRAM devices was done by this company called Everspin Technologies. Now, Everspin Technology is not really a startup because it was a spin-off from Motorola, which broke away into Freescale, which focused primarily on memory technology, and Everspin was a subsidiary. Now it has become independent of Freescale Semiconductors, which focused only on MRAM technology. So as you can see, the first generation of toggle MRAM devices had your magnetic tunnel junction connected to your bit line or your write word line, which provided your oystered magnetic fields was very, very close to your magnetic tunnel junction, whereas the read word line was connected to the gate of your access transistor. So the strategy that Everspin has taken is that it develops standalone memories for niche applications. And how they market their MRAM technology is that it is a memory device technology which offers very high reliability. First and foremost, they promise that the data retention in these MRAM devices is more than 20 years. Not only that, they also promise that these devices have unlimited endurance. This is because the write is not happening through the magnetic tunnel junction, unlike STT MRAMs. So there is very negligible wear and tear of the tunnel oxide of this magnetic tunnel junctions in toggle MRAM devices. However, despite these interesting properties of high reliability that toggle MRAM devices had shown, there was large limits to how well you can scale these toggle MRAM devices, especially because below the 90 nanometer node, the bit density suffers quite a bit, and also the cost per bit is also very, very high. And that is evident from the fact that it becomes very difficult to make toggle MRAM devices which is greater than 16 or even 32 MB. Not only this, the write current that is applied on the write word line, which changes your magnetic tunnel junction's free magnetization layer through oystered fields, also does not scale very well when the cell size shrinks. So next, as we know, there was a move to go towards spin transfer torque magnetic tunnel junctions. While the first generation of magnetic tunnel junctions were in plane magnetic tunnel junctions, where the polarization is along the direction of the deposited free and pinned layers. The latest generation of magnetic tunnel junctions are where the spin directions or the magnetization is out of plane or perpendicular to the deposited thin film of pinned and free layer. This is because the perpendicular MTJs offer much better scalability compared to the in-plane MTJs. And Everspin Technologies, along with Global Foundries, for the first time demonstrated 64 MB DDR3 compatible ST MRAMs, which were built on the 90 nanometer CMOS technology as early as 2013. So this is the cross-sectional transmission electron microscope. As you can see, the metal 3 was taken to be the bottom electrode, whereas metal 4 was considered to be the top electrode, and sandwiched between the M4 and M3 layer was your magnetic tunnel junction. So the microscope image of magnetic tunnel junction is also indicated in this particular diagram. And in 2021, for the first time, Everspin Technology were able to show the first 1 GB MRAM which was completely DDR compatible. As you can imagine, when you are making these standalone memory compatible with DDR, the promise is that you will be able to replace these MRAM devices with conventional DRAM technology. And the positive news is that this replacement of DRAM with MRAMs will be completely non-volatile in nature. Since they will be non-volatile in nature, there will not be any need for continuous refresh, and at least in promise, they will be low power. However, considering that the cost of these MRAM technology is much more as compared to DRAM technology, these MRAM standalone chips have been mostly relegated to very niche applications which require very reliable data storage. Some of these examples are military, automotive, embedded IoT, and space applications, where you can compromise a little bit on the cost. At a little bit higher cost, you want to have memories which will last for 20 or 30 years. So this has been the niche space where Everspin technology has been playing. They are trying to make standalone memory which could be replacement for DDR or sometimes even flash memory, but for very niche, high reliability memory applications. The next set of commercialization came from your major foundry players like Intel, TSMC, Samsung, and global foundries, where now they have started developing a completely different strategy for introducing MRAMs. What they are doing is they are developing IPs or libraries for embedded MRAM applications from the 16 to 28 nanometer CMOS nodes, which you can buy. These IPs you can buy and you can do your own VLSI design and integrate these MRAM devices in your own chip. For example, if you are building a chip for defense applications and you would want your cache or your DRAM or your embedded flash memory to last for a very long time and have very high reliability, you can buy these IPs and get them fabricated according to your specification from these major foundry players. In this regard, Intel demonstrated a very interesting concept in 2019. And to understand this concept, again we have to go back to the so-called energy landscape diagram, which we have been looking at again and again in context of several memories. MRAM technology, the energy landscape diagram, has a global minima in the high resistance state. This is because, as we had seen, that the anti-parallel configuration is stable even at zero magnetic field. This is your most stable configuration, whereas your parallel configuration of low resistance state is slightly higher energy. Now the energy that you have to surmount to flip from your anti-parallel state, which is your high resistance state, to your parallel state, is known as the delta or the thermal stability factor. Now this thermal stability factor is the ratio between this activation energy divided by the thermal energy. And as we have been discussing in all different technologies, if we have a small delta, the retention of the device becomes poorer. It becomes less stable. However, writability becomes easy. Therefore, latencies reduce. However, the same delta, if you make it large, the retention becomes better, but write latencies suffer. And this concept was used by Intel when they integrated STT MRAMs with their 22 nanometer FinFET technology. What they essentially demonstrated is that by controlling the size of the magnetic tunnel junction, you can change the thermal stability or the energy it takes to jump from the anti-parallel state to the parallel state. And thereby, for cell sizes which were less than 55 nanometers, you could engineer a very small delta of roughly 20 to 40 times of KBT. And as a result, your write latencies became less than 10 nanoseconds. Your endurances also improved, but all of this came at the cost of much reduced retention. This is no longer a non-volatile memory. the retention is less than 1 minute. And this is very useful for last level of cache kind of applications as a replacement for SRAM. However, the same technology, if you go to higher size of MTJ, roughly 70 to 80 nanometers, the delta can be increased to more than 60. As a result, the writability becomes more difficult because it becomes more difficult to surmount this barrier and go from HRS to LRS state. Write latency increases to 200 nanoseconds, but the stability improves and the retention becomes more than 10 years. And therefore, just by playing with the size of the MTJ, you can control this delta or the thermal stability factor and have completely different applications using the same technology from L4 cache to E-flash. And this is something which has been shown for the first time and is very unique to the MRAM technology. Also, other major players such as TSMC and Samsung in the same year also demonstrated magnetic tunnel junctions integrated with their 22 nanometer CMOS line, and Samsung showed it with 28 nanometer FD-SOI technology. So currently all your major foundries, as we just discussed, have solutions for embedded MRAMs that you can buy as macros and IPs and put in your design chip as well. However, if you see the current trends in using MRAM technology, TSMC as early as 22 had already moved to the 16 nanometer FinFET technology integration, but all these demonstrations, whether it is from TSMC or Samsung, are not really directed towards classical von Neumann computing, but more for AI accelerators and in-memory computing. And this is something that we will discuss in detail after we understand the fundamentals of neuromorphic computing. So to conclude our section of MRAM devices, we can confidently say that MRAM is the first success story in the commercialization of electronic non-volatile memory space. Thank you very much for your attention. See you in the next class.